Hi guys, welcome to the final class. So today I'm going to talk about a recent work we did in our group. It's called Permutation, Equivariant Structure for Motion. So luckily, Hagai spoke yesterday about equivariance, which he worked with us on this project. So I hope some of these things will be familiar, but still we're gonna talk about it. Okay, so we'll start with a very short introduction, talk a little bit about equivariance and invariance, and then the model, the loss function, and the results. Okay, so first, motivation. I hope you already have this motivation by the last class, but still. Okay, so structure for motion is an interesting problem. Personally, I think it's very interesting, but it also has a lot of applications, and it's a very basic thing for many AI-based applications, like self-driving cars and satellites and robots and so on. So it's an interesting problem. And there are many open challenges. Some of them are quite solved, many of them are not really. For example, there are ambiguities. When we have a bunch of images, we could have many things that can cause ambiguities and make the problem very hard to solve. For example, if there are moving objects or untextured surfaces like metal or shiny things, reflections like in this statue, occlusions. So there are still many challenges if I try to match points, for example, with images of this statue, I probably won't be able to do it with the current methods. End-to-end is another very big challenge in this field. Currently, there's many applications are made of this pipeline of several steps and pre-processing and matching and so on. And there's not a single machine that I just put the images and get an output immediately. And this is something that we are in the group are trying to get to, this end-to-end thing. Runtime optimization can be quite slow, and we would also like to make it faster. And accuracy, I think it's in general for every AI thing and almost everything in computer science now that we can always make it better. And so,
Hodaya, runtime here is for inference?
Yeah, inference.
For training.
Okay, so actually, we're gonna talk about optimization and learning. So these things are different. So obviously optimization can take a long time, and also training can take a long time. The only thing that hopefully is fast is the inference in test time. And we're gonna talk about it too. So how does the problem look like? Also this, you've seen this in the course. We have a group of images, and what we want to output is the 3D points that made this object, and all the cameras that took pictures of these images. So this is what we want to get to. And I will just say that this work does sparse reconstruction, meaning we have this sparse points, n points, and we don't have the real depth of all the pixels in the image, only the interest points. So usually the classical methods either do something that is sequential, that we add an image at a time, and then we optimize it, we perform bundle adjustment and again repeat. And there are also methods that do a global optimization with algebraic constraints. These are the classical methods. There are also many attempts of deep learning to solve this problem. As far as I'm concerned, there's not one that really solves the problem. So there are many methods that try and they do specific things, but it's still unsolved. So for example, this method daemon, it solves for only 2 images, where it solves like a dense depth for one image and the relative pose of the other one. And deep SFM uses the cost volumes, so it involves discrete sampling of different depths, and all these methods are quite limited. Deep SFM, for example, can only work on very small number of images. So we want to try to get in this gap here. All these, many of these methods, what they have in common is that they try to minimize the reprojection error. And you've already seen this. If I have the 2D image point X, and I have P, the camera matrix, and capital X, which is the 3D point, I can calculate the projection of X onto P by this formula. Meaning I multiply P by X and I divide by the third coordinate. And the reprojection error is the Euclidean distance between this point and the projected point. So this is what I would like to minimize. So what is the problem? Why can't I just minimize it? Meaning, assume that I have the image points Xij. Why can't I just find all the Xj that minimize this loss? Well, it turns out it's a very hard problem. There's no closed form solution. It's non-convex, and it requires a very good initialization. So if I just I have a random initialization, I can get to really poor results and get stuck in local minima. So it's not an easy optimization problem. And there also, there could be a lot of parameters. For example, in the data sets that we handle, there could be hundreds of thousands of points and hundreds of cameras. So it's a very hard optimization problem. And now the question is, since this is a very hard optimization problem, maybe the solution that everyone is doing now is just put it inside a neural network and hope that it will be able to find the optimal solution. So this is our first goal, to optimize the reprojection error, meaning I have a specific scene, one scene, a bunch of images taking pictures of the same object, and I want to optimize, find the 3D points and the cameras. But now, since I have a neural network that can solve it, it's very, the next step is taking this network and apply it to novel scenes, and this way generalize, and this could really improve the running time. Okay, so let's dive in. Let's look at the input first. The input to our method is a matrix, a sparse matrix. We'll call it capital M, and its size is M by N by 2. And the rows are each row corresponds to one image or one camera that took the picture. And each column corresponds to a 3D point. In this entry, we have like the X and Y coordinates of the 2D points. And this is a very sparse matrix. And we will denote all the 3D points that are in camera I, C bar I, and all the 3D points, all the cameras that see the point XJ will denote as CJ. And the typical size of this input could be like, for example, in this data set, the number of images is 172, and the number of points is about 15,000. And there are about 15% non-zero values, so it's quite sparse. And a very important thing to notice about this input is that there are a few symmetries. And symmetries are important for almost any application that we have, it's very helpful to use the symmetries in order to make the space of our solution smaller. So Hagai talked about it yesterday, so I won't repeat it, but understanding the symmetries is very important. So what symmetries do we have here? So first we have the column permutation symmetry, meaning if I can have the 3D point here or here, I have the exact same result. And I also have a row permutation symmetry. I can switch rows and it describes the same problem. And the question now is, what type of neural network can we apply on such a data? For example, if we just try to perform 2D convolution on this matrix, we won't really get meaningful results with respect to the structure of the data. So this is the challenge now. So again, Hagai talked about it, but I'll still mention equivariance and invariance. It's not the same thing. Equivariance means that if I have my input and I apply some transformation, for example, I rotate by 45 degrees. If I apply the function before the rotation and after the rotation, the result, I mean, the F and G commute here. I can either do G first or F first, and I'll get to the same result. But invariance is different. Invariance means that it doesn't matter at all. If I rotate the number 3 by 45 degrees, I still get the number 3. So equivariance means that it changes according to the change that I made in the input. And invariance means that there's no change at all. So our network is equivariant, and soon we'll see why. So again, this is our goal. We have this matrix M, and we want to find some function f that decomposes it to the cameras and the 3D points. Now notice that we have row equivariance, because if I, for example, change this to rows, I want these two cameras to change accordingly. Meaning I don't get the same output, but I get an output that changes according to the change that I made. And I also have column equivariance. So if I switch to columns, I want the 3D points in the output to also switch. Okay, now we're gonna see 4 basic operations that preserve what we want, that are equivariant to rows and columns permutation. And then once we have these 4 operations, we can just combine them and sum, and this will be a single layer of the network. Okay, so let's start with the first operation. Let's say this is my input m by n by dl. After the lth layer, I start with a dimension of 2, but then I add the representation of each point gets larger after several layers. So this is the input I have in layer L. And now let's say I take each of this 1 by 1 by dl tensor, and I apply some weight vector W that takes each of these vectors and transforms it from dl to dl plus 1. And this is just a matrix multiplication for each of these tensors. So I actually get in the end m by n by dl plus 1. Now, is this thing equivariant to row permutation and column permutation? Yes, for both, because it's quite simple to see that since we have the same weight vector W1, if I switch rows, they will be switched here, and if I'll switch columns, the same. So this thing is equivariant. Now for the second operation, let's say that we average all of the entries in the first and second dimension, and I get a tensor which is 1 by 1 by dl. And then I apply this weight matrix to get a new representation, and finally expand it so that it will be in the dimension of the first of the input. So is this thing equivariant to row permutation, column permutation? Yes, and it's even invariant. Why is it invariant? Because once I average over the rows or over the columns, I actually lose all the information about the order. So it doesn't really matter what order the rows have or the columns, they still get to the same output in the end. And the third and fourth operations are very similar. So the third one, we average over the rows and then apply linear layer on each of this one DL tensors. It's just matrix multiplication. And finally expand again to get m by n by dl plus 1. And since I average the rows, it's invariant to the row order. I lose all the order of the rows, but I preserve the order of the columns.
What kind of expand operation you have?
Okay, so actually for memory requirements, I don't actually repeat this tensor. I just, in the end, I sum over all these operations, and in PyTorch, when you sum, it expands it expands them to the larger size. So you'll soon see. I have these 4 operations, and I sum all the outputs. Okay, so the fourth one, I average over the columns, and again, expand. Okay, so to summarize, we have these 4, we leave the input as is, and then we average over the rows, over the columns, and over both of them. And we apply a very simple linear layer on each of these things. And finally, I sum. So Shian, about what you asked, I sum over this and this and this one and this one, and PyTorch expands them automatically. So this is the one layer which preserves the structure of our input. And now we have a bunch of these layers, one after the other. And the question is now, how do we get the final output that we want from the network? So again, we average one time over the rows to get the points, and one time over the columns to get the cameras. So here, it's exactly like we've seen in the previous slide. We average over the first dimension to have n by dl, where n is the number of points, and then just apply this linear layer. It's actually an MLP here, it's several layers, to get to n by 4, which is exactly the points that we want. And here we have m by dl, we apply an MLP to get m by 12 and get all the cameras that we want. Okay, so this was all the structure of the network, and now how do we optimize it and what is the loss function? The loss function will have 2 terms. Reprojection loss and another loss on negative points. And the reprojection loss, it's what we've seen many times and in the beginning of the lecture. This is actually what we want to optimize. The problem is that if the 3D point X is in front of the camera, this loss has a meaning and it's what we want to optimize. However, if the point is behind the camera, it doesn't really help us converge, because there could be a situation where the point is behind the camera, but still it projects exactly to the right point. So the reprojection loss will be low because it does project to the right location. But we know from how we understand the world, we know that the point needs to be in front of the camera, and it's not the solution that we want. So this thing can be very difficult. If some of the points are behind some of the cameras, this thing could get stuck. So we need to solve this. And how do we solve this? We want to encourage the points to be in front of the cameras. So here's a reminder from lecture 1 when we talked about the depth of points in a specific camera coordinate system. So let's say we have the camera P, and it's comprised of a 3x3 matrix M and a 3x1 vector P4. And let's say that it's normalized, meaning the determinant of this 3x3 matrix is positive, and the third row of this matrix has norm 1. So for a calibrated camera, this thing is just a rotation matrix. And the rotation matrix already fulfills these conditions. It has a positive determinant, and the norm of the third row is 1. But if the camera is uncalibrated, then we need to normalize it by multiplying by the sign of the determinant and dividing by the norm of this row. And this will give us a normalized camera. Now, once the camera is normalized, the projection of X to P is this, and the depth in the projection of the point to the principal axis is this W, which is the third row of P multiplied by X, P3X. So to summarize, we want to make this thing positive. What?
Not always you want to make this positive, only in the case that X is in front of the camera.
Yeah, okay, that's a really good point, because in real life, maybe like, for example, if you have a self-driving car, so a lot of points of the world are behind you. However, in these data sets, it's very rare. Mostly the points are in front of the cameras. It's like cameras taking pictures of an object that's in front of them. So maybe you're right that if it's a self-driving car, we need to find a better solution. But for us, we did need to encourage the points to be in front. So what do we do here? First, we normalize the camera P, like we said. And then we want to encourage this thing, P3X, to be strictly positive. Okay, so how do we do that? So if the depth of the point is negative, instead of applying the reprojection error on the point, we apply a hinge loss. We take some positive small constant, we call it H. And if the depth, meaning W, which is on this axis, if it's negative, then we have a corresponding loss. So to summarize, the loss, which is the unsupervised. So for point Xij, if it's in front of the camera, we have the reprojection loss. And if it's behind the camera, we have this hinge loss. And we average over all the valid ij, meaning all the points that are non-zero in the input matrix. So to summarize, this is the network architecture. We start with these images, and we have the point tracks. So this is the input matrix, and we apply the permutation equivariant layers. And finally, we split it to the points and the cameras. And now I wanted to say a couple of short things that, I don't know, maybe they could be useful to someone, like in general, not specific to our problems, but it's things that we've encountered. So we had an optimization challenge where if a point is in front of the camera, even if the depth is positive, it could be quite small. And in general, when we optimize for something that is in the denominator, we have a risk of that it will be small, and then the gradients will explode and be very big. And we noticed that this thing makes the process less stable. So our solution was to normalize the gradients we normalize the gradient of px to have a norm 1. And this helped make things more stable. So I think it's in general like something that's, we used here hooks that you saw in the deep learning course. Another challenge that we had was a memory challenge. We had hundreds of cameras and tens of thousands of points. And after several layers, this thing gets really huge and there's not enough memory. So we try to use the sparsity of M. Now, since M is very sparse, it has only like 15% non-zero values. So PyTorch has some sort of beta sparse tensor implementation. So we tried to use it, but it was very big on the runtime. So we implemented a sparse tensor class that was made specifically for our needs. It had only functions that we needed to solve. So it was much more efficient. And that's it. It's like an idea. Maybe it's something that you can use if you ever encounter these problems. Okay, so some results of the optimization. Wait, sorry. Okay, so some results of the optimization. I think really nice results. I'm objective here. So compared to other methods, it was as good as the other methods. The most significant competition was VARPRO, and it reached in all of them, almost all of them to about the same optimum. However, we did have some failure cases. And I think the thing that is common to these failure cases is that they were a small number of cameras and in a circular motion around the object. So you can see here, the green is the ground truth cameras and the red is our prediction. And for some reason, the network had a really hard time converging to this situation. So that's a failure case that we need to understand what's happening there and why performing this perfect circle of a small number of cameras is so difficult. So these results are all optimization, meaning I have a single scene and I optimize the network to output the correct 3D points and the cameras. But learning, optimization is interesting by itself. It's a new architecture. It's a new way of solving this problem. However, this could be quite slow, like many other optimization problems, including the optimizations, the other methods that we compare to. A lot of them are quite slow. For example, VARPRO, all these things that are missing, it's that it took too long. This was like 12 hours to run. There are methods that are faster, of course, but still optimization is not extremely fast. So we wanted to try learning, which is a complete other new difficult problem. And the advantage is that after learning, inference is very fast. But learning imposes many new challenges that we don't have in optimization. I think that the hardest problem is that there was huge variations in the data set. There are some that are very small, like you can see even here. This has like 18 views, but these ones have, I don't know, 140 or something. You can see here. There are some with 14 and some with 368. And the number of points is also has huge variations. Some of them are 7,000 and some 130,000. So this was a very big challenge. And another challenge is a challenge that is general to learning is that if we have large amounts of data, we obviously need to make a bigger network than we used for optimization. However, if we have a network that is that has a larger capacity, it also can be very hard to generalize. And so it's hard to find this thing, where in optimization, we don't have this problem. We just, if you take a huge network, you'll be okay.
So,
yes.
How did you choose the architecture for each data set? For example, and if you know what happened in like specific data sets, for example, in the previous slide, we see that there is a very large one, the Buddha statue, and it seems like the method wasn't like, it's, yeah.
Yeah, so we actually used for all the optimization settings, we used the exact same architecture and the exact same optimization process, same loss function, same hyperparameters, everything the same. You're right that it might not be, like, for example, if I want to solve only this, maybe I will use a different architecture. But we wanted to have like one ring to rule them all. I don't know, like one architecture, one optimization process that actually did manage to solve almost all the scenes. So you're right that maybe.
Is there a common thing like in the data set that you succeeded to solve or like failed?
What was the question again?
If we know what was, if there's a common factor between data sets that we failed or succeeded to solve here.
Yeah, so the common factors from what we saw, and we really tried to solve this thing, we worked on it quite a lot. The common factor is circular motion. Like this, I think this example is really captures it. The perfect circle was very hard to converge to. Semicircles were fine, or even like if it wasn't really closed, and also small number of images. This was also hard. Like the most stubborn data sets were like this one, and another one which was like 10 cameras looking away from each other in a circle. This was like, this was the common factor, basically.
Thanks.
Hodaya, I also have a question. Please let me know if it's out of context, but how you compare your method to NERF method, neural radiance fields? Because also there is like a statue that you want to find a 3D structure of it from different point of views.
Okay, so there are, to NERF, there are two main huge differences. The first one, the task is different. NERF does a novel view synthesis. It doesn't create a 3D structure. In fact, to get from NERF the 3D structure, it's quite a lot of work. It's not trivial. They don't give you, like, since you integrate over densities, you can't really know what is the object. It's not trivial, so it's a different task. And the second, NERF uses ground truth cameras, meaning they take the ground truth cameras and then they optimize for this novel view synthesis situation. And we also want to find the cameras. We don't have any ground truth information, and we want to find it from scratch. So it's a very different approach. There was a method called NERF minus, and it was similar to NERF, but they also they didn't have the ground truth cameras. They also found them. However, it only worked for cases where the cameras are looking like without rotations. All the cameras are looking the same way. So it's very limited. So there's no really a method that solves this perfectly.
Maybe the only similarity here is that both are end-to-end methods, deep methods, but.
Okay, so I wanted to talk about it in the end. We'll get to that. We'll get to the end-to-end thing. Okay, so the learning, we divided the scenes to train, validation, and test. During training, since we had the very large variations in scenes, we had to sample rows. For each scene, the data loader sampled parts of the matrix. We didn't train on the entire huge matrix. So this also, it's sort of a data augmentation even. It allows us to create more data samples with the same training set. And it made all the examples smaller. And then we performed inference. And finally, after the inference, we added a short fine-tuning stage of a single scene optimization. So what does it look like? So we had this inference, which is like a few milliseconds, but we noticed that we still didn't have the results that we wanted. And we needed to add this short fine-tuning step, which really helped things converge much better. And in order to compare the fine-tuning, you could say that fine-tuning maybe solved it by itself. We just did optimization. So what did the inference do? So in order to show that inference does help, does give us improvement, we compared this fine-tuning with short optimization by itself. Meaning we compared inference and short optimization and short optimization alone. And we can see that short optimization alone doesn't do anything basically. I mean, a reprojection error of 100 is basically nothing. However, after inference and fine-tuning, we were able to get to the same, Colmap is the current state of the art in this field. Okay, we'll maybe talk about it soon. So we managed after inference and short fine-tuning, we managed to get to the same optimum. And this is a visual example. This is the inference and fine-tuning and short optimization, which is, like I said, nothing basically. Okay, so to summarize, we use the neural networks to solve a very complicated problem. It's non-convex. Usually it needs a very good initialization, and we didn't use any initialization. We solved it from scratch. And it has many parameters, like you see, up to hundreds of thousands or even millions of parameters. If we have like 400 images and 200,000 points, it's a huge number of parameters. And we were able to generalize to new scenes, which is not trivial. Inference by itself is very fast. It's in milliseconds. The problem is that we added this short fine-tuning. Hopefully we will be able in the future to have only inference and solve problems in a very short time. The learning was unsupervised. There's no ground truth required. However, the limitation, and Nadav, you talked about the end-to-end. So this is really the goal here, getting to end-to-end, because this input matrix, the point tracks matrix, it requires pre-processing. I don't have it from the images online. I need to do point matching. And once I'm required to do point matching, then I have all sorts of problems in point matching. For example, like what I said in the beginning about ambiguities. If I have reflection or non-textured objects, this whole thing is very problematic. So the end goal is to take what we did here and to add another component in the beginning that will work directly on the images. And hopefully this will get to the end-to-end scenario. So this is the goal. And that's it. Questions?
Just like a general one. So the next goal is to generate the initial matrix we saw in the beginning.
Yeah, generally, yeah. The problem is, okay, so I will rephrase it. The goal is to have a dense reconstruction from images. So this is sparse reconstruction, and it doesn't take the images as input. So the goal is to take the images as input and have a dense reconstruction. So the matrix is like a component or something that might help us get to this end-to-end part, but we do need to figure out some things on how to incorporate it, like I said, to make it really end-to-end. So it's not trivial at all. Like, hopefully we'll solve it.
There. As I understood, you don't put input as an image, you just put pairs of points in the beginning of the network.
What did you say?
That in the beginning of the network, your input is just pairs of pixels, not images.
Right, exactly. It's point tracks, like matching. And using the images themselves, it has a lot of advantages because it allows, like I said, a dense reconstruction. Once I have an image, I can have a depth map over this image, and this gives me for each pixel its depth. However, it's much more difficult. So there's still not a method that does this, like takes images and outputs 3D reconstruction dense. There are a lot of, it's like NARC presented in the seminar in Vision. So there's a very big pipeline, many other methods. We take a network that does optical flow, and this network and this thing, and do optimization in iterations and so on. So it's a big challenge.